So yesterday we completed PCA or the principal component analysis that to do feature extraction, that is mapping from a third dimension feature set to a lower dimension projected space of feature. And we saw that by PCA is basically nothing but the first and second. So if I want to reduce from say like the original d-dimensional data to two-dimensional data, so it is nothing but the first and second eigenvectors of the uh, covariance matrix of X. So now there is another method called feature embedding. I think there was lots of queries also yesterday regarding the dimensions of the X, W, and Z. So feature embedding is, I'm deviating a little bit from the PCA first. You must have heard about it in the artificial the neural networks. So have you heard something called the Watt-to-Vec? Any of you? We use the terms word embedding, right? In artificial neural networks, if you have done anything with that. So can anyone please respond with yes, no? Hello? Hello?
No, ma'am.
Mm, okay. So, when you do any kind of coding with even with basic deep learning or neural networks, you will see a term is coming again and again. If you are doing the language, natural language processing, these will be the word embeddings or sentence embeddings or character embeddings. And if you are doing the image processing, those will be image embeddings. So embeddings will come again and again in machine learning modeling or neural network modeling. So what are embeddings? So embedding is also a method of projecting from a higher dimensional data to a lower dimensional data. But to give an example, our case, say I have originally n dimensions, sorry, n data points, and each was represented by d dimensions. So d is the, as we have seen yesterday, that d is my actual feature set, feature dimension, or the length of the actual feature vector, which can be very high. So till now, what did we do in PCA? We said we are extracting the eigenvector of variance of X matrix, which is actually X transpose X, which is a D cross D matrix representing the covariance of features if the mean is centered. Okay. By D cross D, if X is n cross D, X transpose is D cross n, so D cross n into the n cross D. It will be a D cross D matrix. So PCA actually uses the eigenvectors of the D cross D matrix for projection in a lower dimensional space. While this X into X transpose, which will be an n cross n matrix, represents on the other hand the pairwise similarity of the instances. Pairwise similarity means we have looked into the distance measures, the Euclidean distance, and how we can evaluate like how two data instances are similar to each other or not. So feature embedding techniques uses the eigenvectors of this X into X transpose, that is this n cross n matrix. So what is the advantage, or why do we do feature embedding, is that it directly gives the coordinates after projection. So we, whenever say we map a data set, say from 100 features uh, two dimensions by doing PCA. So we are actually visualizing the data, but we generally do not take the two-dimensional feature vectors to as coordinates of the real data points. But for feature embedding, what we actually do is that after learning the embeddings, we directly use those embedding vectors as the coordinates of my original data instances, or my data point is kind of all the machine learning modeling then is done on the embedding vector only. Okay, just a moment. Okay, okay. Yeah. So So this is the difference between PCA and feature embedding. So PCA is a form of feature extraction, and but when we are using the eigenvectors of the covariance matrix and feature embeddings, we are using the eigenvectors of the pairwise similarities of instances matrix.
But how did we calculate the covariance?
Sorry, Yeah, can
How are
you,
we calculating the covariance?
we are calculating the covariance between features like based from the
I mean, like if
statistic.
n is the data matrix where the n number of rows are for n data points and d columns are for d features, then how can we get covariance by just doing x transpose x?
X transpose X. Okay, so basically X transpose X is nothing but if you when you do the matrix multiplication, if, so it comes down to like the scalar multiplication or the scalar products between the features, right?
Yes.
Yes, yes. So that is how the in the vector definition the covariance is described. So that's why, like, if the main is centered, then uh, that matrix will represent the covariance of the
You
feature.
mean
So
the mean value is subtracted from each
mean
term?
value subtracted, yes.
But
So
then
that,
shouldn't we divide this by n?
no, we shouldn't divide this by n. See, actually, this mean is not kind of we are not doing a summation and then dividing by n, right? So this is the like this center, this first order momentum, second order momentum. So that's how we are calculating.
Okay, okay, ma'am, got it.
Okay. Okay. But good question. So see, actually, what happens? These things, these are have been assumed and for so long that rarely we actually go into this kind of discussion, which is very relevant if someone is learning this for the first time, that how these things are happening. So and then instead of just copying it into the memory, it will have a better impact. So nice question. Okay, so uh, so what happens is that why do we use feature embedding? So sometimes the pairwise similarities are important for doing calculations. Say for example, I am giving time and again the example of something called the word embedding. So in that case, let me give you an example. Give you a snapshot of that. What do I mean by feature embedding in a workspace? I guess I have it open, but let me Just give me a moment. I need a picture. আরে yes. So what happens is that say I have a word data set or a natural language processing data set. Okay. So generally then how do I represent each word? Say my atomic units, my xi value will be so I want to represent my whole vocabulary. Say I have a large text, large collection of text. Large collection of text can be example of um, suppose I have scrolled all the news articles related to sports for past 5 months. So that means I will have a large volumes if I collect it from multiple sources. So now I want to do some modeling on the large text corpus. Okay. So now how do for doing the very basic modeling, what do I need to do? My computer cannot understand text, so I need to represent text as a set of features. Correct? So how do I now come up with text as a vector or text as a set of features? I say that okay, my each atomic unit of text are the words. So I come up with the words as a vector. Each word will be represented as vectors. Why words? Say if I have say like 5,000 news articles scroll that large number of text, but it will be very fair to assume that the vocabulary will be very limited, right? It is not that we have an infinite number of words. It will be order of 5,000, 10,000. Okay. So that means I have distinct 10,000 data instances whose combination permutation represent all my text. Okay. But now these 10,000 and also keep in mind one thing. These 10,000 words, they are not exactly always independent of each other because we know that which word will come after which word, there is a probabilistic dependency, right? Not every two word combinations are equally probable. Say good morning, for morning to come after good is more probable than bad to come after good. So that's how we do very basic language models like when we work with text data. If you recall, I discussed it when we were discussing the Bayesian net or the Therian Markov. I said the Markov chains. Okay. So now how do I represent each word as a vector? I said, okay, fine. I will use something called a one hot encoding. It is nothing but, as the name suggests, it will be only the one that is one hot. Like say my each word. What is each word? Each word is one instance of say my 5,000 word vocabulary. So I have a 5,000 length vector for each word for which exactly only the one entity is non-zero. All the rest will be zero. Say I have say like three words is my vocabulary. Machine learning class. So then if I make a three-word vector to represent each three of the words, so in the first one it will be the 100, second one it will be 010, and third one it will be 001. First one will represent machine and the landing and class places will be 0. Second one is representing machine is 0, learning is 1, class is 0, and the third one is representing machine is 0, learning is 0, and class is 1. So now if it goes for say like 5,000 vocabulary, 5,000 word vocabulary, so you can understand for each of the 5,000 vectors, only exactly one element is only one and the rest are zero. So it is a form of encoding. We are the encoding as text data into a numerical data. We are not doing any kind of modeling right now. And as only one place is non-zero, that's why it is called the one hot encoding. Now, as you can understand, by working with this kind of vectors, the problem is that it is a very, very sparse vector. So actually my input matrix will be a very sparse matrix. Okay. So for that, what do? We then use feature embedding, because my all these my one hot sparse vector, they also represent, like if I do the scalar product, they will represent the similarity which will be actually zero in this case. So I cannot work upon them. So that's why I go for this feature embedding. That is all this sparsity. I am projecting it to say like this from 5,000 dimension. I am projecting it to 100 dimension or a 300 dimension space, which is this space. As a result, what becomes that this sparsity, it becomes very compact. It's like, you are clamping all the 5,000 relations and dependencies on the 300 dimension space. And then we can directly use this vector as a representation of each word. For each word, we learn this embedding by some method. I am not going into the details right now. And we basically use now only these vectors as a feature vector for each word directly. And then we say that if two words are how similar with each other, by doing a scalar product between these two learned feature embedding vector. Okay, so that's how feature embedding works. In most of the time, we directly, like, it is learned on a measure of similarity. So in this case also, this network that you are seeing, like, it is mentioning only 3 or C can be 3, 4, 5, anything. The reason being that these embeddings are learned based on, like, say I want to learn the embedding for the word X, then the input will be X, two words which are before X and two words which are after X, to consider like how X co-occur with other words. And this measure of co-occurrence is actually a measure of similarity closeness in the natural language processing terms. Okay, so that's how these pairwise similarities are also captured into the learning of feature embedding. I guess I was able to convey the message. So, any question till now? Okay.
Ma'am,
Yes.
like after doing this dimensionality reduction, like why can't we treat the values of uh, the principal components in the reduced dimensions as new features?
We treat in some cases, but generally we use PCF mostly for data visualization and data understanding. In some cases, we use the PCA transformations as directly as the features. See, this kind of see, the thing is that theoretically you can use any of these as the new features. Now, when you actually go on doing different machine learning modeling, it is kind of the trick of the trade. So you learn that when to use what kind of transformations. Okay. So was I able to answer your question?
Yes, ma'am. And like while designing any deep neural network, so
Yes.
is it always the case that we first do the dimensionality reduction and accordingly decide the number of neurons in the hidden layer?
Uh, uh, Actually, yes and no. There are some neural network models which are trained from scratch, which means that they start with their your raw text data or raw words. Then by the end-to-end training, it learns the embeddings. But of course, you need to specify the dimensions of the embedding. So because you are constructing the neural networks, so the kind of dimension, so you will put in the specification, and dimension is nothing but the number of neurons and their connections. Okay, so that's determine what kind of what in what kind of feature space you will learn your the neural networks. And see, generally what happens, these deep neural networks, the field is, what happens, you will not uh, suddenly go and make a new neural network from scratch, particularly if that is, truly it has 3 4 5 layers. What happens for many of the cases, there are many tried and tested neural network, the architectures, say made by different reputed research groups, made by Google, made by CMU. Okay, so generally that architecture is very standardized. So you use a 300 dimensional feature embedding. Okay, so we, for most of the cases, we repurpose that. So the what kind of embeddings are to be used, what dimensions, those are tried and tested, and more or less you will see for most of the things, those are pretty standardized. So you can tweak, say, like 100 dimension more, 100 dimension less, but not some really drastic changes. So this was the first thing, that where the all the embeddings are learned within the training itself. The second is that I can also build a neural network which will, where my input will be pre-trained word embeddings. What does pre-trained means? Say if I nowadays there is uh, a term called BART. You will hear everywhere the BART embeddings, pre-trained BART embeddings, BART learnings, and all. So BART is a transformer model. I am not going, so just for the naming sake. So what, why we use pre-trained BART embeddings? Because it is a very large models with a lot of parameters which will not be very economical to train every time we try to use a neural network on a data set. So on a fairly large and generalized, and there are some specific data sets also on which BART is trained. So this model is trained, and some embeddings, the word embeddings or feature embeddings have been generated and stored and have been made available for public use. So we take those embeddings and then we feed those embeddings directly in smaller neural networks which we can train over different epochs, and maybe the neural networks will be fine tuned for our particular task, and we get the output from them. Or even for, say, What2Vec. Google already trained What2Vec on a large data corpus, and the embeddings are freely available. Okay, so we do not go on training it every time, although training What2Vec won't take much time on a data set. But we took those fairly general embeddings for, say, I have a general purpose task, a plain text news categorization. So I take those word embeddings and I learn my model on them. The useful thing is that it is not that on the word embeddings I only need to train deep neural network. I can do technically a classification also using support vector machine on the word-to-vec embedding. Okay. So was I able to answer your question?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Thank you. So we completed in dimensionality reduction, PCA and feature embedding. The next the next method is called factor analysis. See, I am just trying to cover some commonplace methods which you will come across in future in different statistical, quantitative or machine learning modeling. So in factor analysis, what do? We assume my X is a collection of my X is made up of some latent factors which we call Z. So we try to find a small number of factors Z which when combined will generate X. So in this case, I am assuming very intuitively, say if X is my d-dimensional feature vector, my d-dimensional vector is actually a combination of latent k factors. So if I represent the x minus mu y, like x I am centering around the mean, so it will be a linear combination of say vi1 z1 vi2 z2 vik zk. So a linear combination of the k latent factors plus some epsilon. So where these zi's are, as I said, for the latent factors. Why latent factors? Because they are not explicit. They are not any particular feature. I am just assuming my each feature vector is made up of some latent factors which I am not able to directly observe, but if I assume it and if I try to do a mathematical modeling to understand how these factors are combined, I can do that. And this Z is the Z have unit normal distribution, that is mean 0 and variance 1, and covariance between Zi and Zj is equals to 0. That means they are orthogonal. Okay. And this y, this epsilon, see, we are assuming there are some latent factors, and actually we are saying these factors all combined together will make up X. But of course, we know that data sets are not that perfect, so there will be some hidden noise. So these noise sources are modeled by this epsilon, like what we cannot accommodate in the latent factors. Okay, so these epsilons are also orthogonal to each other, and this epsilon and this z, that is also orthogonal to each other, and this has a fixed mean. Okay, each epsilon. So each noise source has a fixed mean. So these and this vi, these coefficients of z, this is called the factor loadings. That is how much each factor is contributing to make my x or the feature vector. So what is the difference of the factor analysis with PCA? What am I doing? See, what was I doing in PCA? I was projecting from a higher dimension d-dimensional space to a lower dimension k-dimensional space by the help of this weight set W, which are the eigenvectors of the covariance of X. So in PCA, we are learning Z from X, like because Z equals to WTX minus mu. In factor analysis, we are saying that there is a latent factor space already, which is k-dimensional, and by a transformation on them represented by V, which is the matrix of factor loading, I can get the original feature d-dimensional feature vectors of X. So it is kind of learning from, it is going from Z to x. Although in both the cases we are having x only, and we are assuming either x is projected to z or z combines to make x. But mathematically, in the first one, we are learning, from x to z, and in the second one, we are going from z to x, because here the equation is x minus mu equal to vz plus epsilon. So, clear till this point?
So, ma'am, which method is better in terms of distinguishing them?
See, actually, these methods are used, so they are not better or worse. They have their own specific areas of application. If you see in if you see in the many statistical modeling, especially for this quantitative data analysis, like doing some surveys, some feedback, and qualitative data, quantitative data, lots of time factor analysis is used. Whereas when you are projecting from higher dimension to low dimension for data visualization after learning a classifier, or after, for to learn, say, a classifier or a regression model or a clustering model in a lower dimension space for the sake of computational complexity or other things, we go for PCA. So both of the methods, like all of the methods, have their own scopes of applications. And as I have said, like, as you keep on working with them, you will automatically like gain that understanding that when, where should I try with what kind of method. So was I able to answer your question?
Yes, ma'am. But like I have another doubt that like if you
Yes,
have a big data set, then
yes.
we can also do dimensionality reduction by doing simple calculations like finding the mean variance of the data. So like how do these features compare with the features that we get by doing PCA or factor analysis?
I didn't get you, like which features compared to PC and factor
I
analysis.
mean, we could also reduce the dimensions by finding the mean of the data and treating that as one feature, finding the standard deviation and treating that as another feature. So, some simple statistical feature.
Okay, so to answer your question, first question is that when you are doing the mean and standard deviation on each feature column, you are actually, you can reduce the magnitudes in terms of the features, but are you reducing the total number of features? Are you reducing the dimensions? May not be from what you say. And to answer the second thing, so what are all these? What is we are doing in factor analysis, what is we are doing in PCA. So it is nothing but we are learning only on the covariance matrix on the feature set. That is what we discussed right now, right? That we are we when doing PCA, we are finding out the eigenvectors of the covariance matrix only. So basically, we are still learning on the mean and covariances of the features, as you said. But as we are choosing the eigenvectors like k eigenvectors, so I am projecting from a d dimension to k dimension. And this method is mathematically sound because it shows that my information loss is minimized. Okay. So this is the relation. What you are saying may be a very crude method to do a magnitude, this whole feature spectrum reduction or even the number of feature reduction. But these are the mathematically sound models to actually project from a higher to lower dimension space.
Okay, ma'am.
Okay. Okay. So if you recall how we were doing in PCA, so we are finding out the orthogonal the eigenvectors. This is an example for two-dimensional data, and we are kind of rotating and stretching from this the original dimension now to this the eigenvectors dimension. We are doing the exactly opposite in the factor analysis. So in factor analysis, we assume that we start with the data, like all my data are combinations, all my feature vectors are combinations of some latent factors which are orthogonal to each other, and then these latent factors are combined, so my data point is generated in my original feature space. So clear till now?
Yes.
Um, Second, it is a method called singular value decomposition, and just give me a moment. Let me see that whether I will do this. Okay. So we completed PCA, feature embedding, and factor analysis. Now this is also a method of dimensionality reduction, but actually it is used heavily in information retrieval as a modeling for as a representation to learn further machine learning models on my dataset. So it is called the singular value decomposition or SVD. It is dependent on a method called the matrix factorization. So I am not going into the more details. Actually, a whole 2 hour lecture can be taken on the singular value decomposition, but I will. There is a good reading material. I will send you. So, what singular value decomposition is? This X is my feature matrix n cross D, if you recall, where n are the number of data instances with the number of the rows, and these are the columns where each column represents a feature. Mathematically, we decompose X into product of these three matrices. V, A, W, T. In this case, it is V, A, W, T. In some cases, it is V, lambda, U. So, different notations can be used, but it is the same thing. So, that's why it is called the decomposition. So, I am decomposing one matrix into product of three matrices. What is V? V is an n cross n matrix which contains the eigenvectors of the matrix X, X, T. That is the pairwise similarity matrix. W is a D cross D matrix which contains the eigenvectors of X, T cross X. That is the covariance of feature matrix. And this A is an n cross D matrix. Why n cross D? This is n cross n into n cross D. It is n cross D. W is D cross D. So the n cross D into D cross D is n cross D, and we get the original dimension of my total data cross feature matrix. Okay, and this A equal to n cross D are the singular values on its first k diagonal. So actually this is a difficult definition written. So let me okay. Let me just complete the slide part first. Then I will look that whether I can quickly have a better explanatory slide. Okay. A are basically, see, this is a matrix. We are taking the eigenvectors of this matrix, and also we are taking the eigenvectors of this matrix. So both of them have some the eigenvalues too, right? So A is actually the root of R for product of the eigenvalues of each of the matrix, and that is only along the diagonal, because we know that the eigenvalues are just scalar values, so they will be a diagonal matrix, and this root over these the eigenvalue squares are actually called the singular values. So because A is in the middle, which is a diagonal matrix containing the singular values of this xxt and xtx, that is why this decomposition is named as the singular value decomposition. Okay, so when we start with A actually all the D diagonal elements in A have some singular values. Then where do we do the dimensionality reduction? We first decompose X and N cross D matrix in this component of three matrices. So A still has D number of diagonal elements. Now I choose K, that I want to reduce from D to K. So what do? We keep the first K diagonal element in A and we make all the other elements as 0. Say for example, if my original feature set is say 5000, so typically A will have 5000 diagonal element. 5000 is not my data instances, 5000 is my feature number. So from that I want to uh, come up with a dimension of 300. So I keep the first 300 and I make the rest of the 5000 0. So now actually A is only the non-zero elements are the K diagonal elements. And why only the first K or first 300? Because these eigenvalues or the singular values, they are sorted in order of their magnitudes from the highest to lowest. So basically we are taking the first K highest singular values. So now what happens when I only keep the first K and make the rest 0, and when I recompose the matrix, so from X I divide it into three matrix, I make the D minus K element in A 0 and I do this multiplication once again to get a new X. So now we get an X which is dimensionality is K and not D. Okay. So this K is called the rank of X. Was I clear how it works? I know it is difficult and
So,
it is,
ma'am, we have to find A by substituting the values of V and W in that equation, and the A matrix will come out to be diagonal, right?
yes, A is diagonal matrix.
And then we have to force some of the diagonal elements to be zero and again solve for X.
Yes. So actually, mathematically, you need to do that, but there are inbuilt library functions for singular value decomposition. Okay.
Ma'am,
Yes.
here V and W matrices are fixed, right? So, and X is also given. So, will not be the A matrix be unique?
Yes. Yes. The
So,
A matrix.
where from will
Yes.
the K, the number K come into play?
Yes. So K is the number that we decide to which smaller dimension space we need to project. Say D is my original feature space. So say for example, you have housing price market, you have 10 features. So that means now your each feature vector is having 10 dimensions. You said no, I want to work only with 3 dimensions. So you need to reduce it from 10 to 3. So this 3 is the K. So K is the reduced dimensional space on which we want to project. Okay.
So, ma'am, if
Uh,
original dimensions are 10, then we solve A, which will be 10 by 10 matrix, but we will only
Not,
consider
not,
first three rows and
not
first
10
three
by 10.
columns.
Not 10 by 10. It is the n cross 10.
Yes, so we will only consider the first three columns.
First three diagonal elements. Okay.
Okay, yes.
It will be a diagonal matrix. So first three diagonal elements.
Ma'am, but here we cannot choose k, right? Because you have written where k is the rank of x, so that will be a particular number. Like if the rank of the matrix is 5, then we cannot choose k equal to 3.
No, see, it is not always the rank of k. Actually, we can choose k, and there is a method to choose k. When actually we use it for the dimensionality reduction. So you can start with the rank of k, but it's not always a fixed number.
Okay, ma'am.
So I will get the reading material on this. Okay, just let me complete this slide, and I will show you in like online only. Yes, anyone asked anything? So actually, matrix factorization is nothing but decomposing the one matrix they, they, into two component matrix. So say I have X and I decompose X into two component matrix F and G such that F is an N cross K matrix and G is a K cross D matrix. So product of these two matrices will be this X matrix. So what is happening? See, this K is a reduced space than X, and it is kind of very very similar to this, right? Factor analysis. So in this case also we are saying this, there are these k latent factors. So in the matrix term, we are decomposing or we are factoring a matrix such that a matrix X, which is of dimension n cross D, can be expressed as a product of two matrices, which in between dimension k. So basically, you see that each element of X can be expressed as this product of this F matrix element and G matrix element of K, like K products, sum of K products, K dot products, okay, or K the elementary multiplications. So this singular value decomposition and matrix factorization, they are used in one of the very well-known information retrieval paradigm known as the latent semantic indexing or latent semantic analysis. As the name suggests, these methods are used to understand the semantic relationships within text. These are predominantly used on text data within text, which are latent, which are not apparent, but through these matrix operations, it is understood that it will capture the latent semantic relationships present in the text, and that is utilized in many downstream tasks like information retrieval, like concept mapping, like to understand text cohesion. Okay. Any question? So let me try to find. So I am giving this PDF in the Teams. If anyone is interested about knowing more, and this also contains a really good description on the eigenvectors and eigenvalues and the characteristic equation of a matrix. So because we are using these concepts so much, it will be really helpful. Okay, so and it also contains, like, it gives a very detailed description of what do we mean by the matrix decomposition, that we are doing the singular value decompositions, right? So what do we mean by that? Why, if you recall in spectral clustering, we said the Lagrangian, sorry, the Laplacian transformation is a positive semi-definite matrix, and we discussed why it was required to have a positive semi-definite matrix so that all the eigenvectors are orthogonal to each other. So all these are discussed here very nicely. And then the singular value decomposition itself. Okay. As I said, we have seen, like, V and W, here it is represented as U and V. Okay, and how we actually do singular value decomposition, like the question you were asking, how we are doing dimensionality reduction, how we choose how to reduce dimensionality, how to do these low rank approximations. Someone asked, like, if k is the rank of x, it will be a fixed number. So actually, how do we come up with k? So all these things are there. Don't worry, I am not going to ask you question from this complex mathematics, but please have a go through in this document. It will really help you to build your foundation. Okay, because it is from the information retrieval book by Chris Manning and others, so which are one of the, like, iconic textbook if you are if want to learn the information retrievals. Like, we are following Itamalpa for machine learning, which is again, the widely used and iconic textbook. Just like this deep learning books by Hinton and all. And it also shows, like, how we can use this in the latent semantic indexing, actually, for our text data, how it shows, how it actually extracts the latent semantic relationships and the relationships between concepts and all. Okay. So just have a go through with it. You will not understand all the mathematics, but I am sure the way this chapter is written, you will be able to understand the basic concept. So I'm just posting it in the general channel, okay? Uh, uh, Not in the class material and all. So, okay, so any question till now? Hello? So any question, anyone? Okay, so let us move on. So I will stop the dimensionality reduction with this uh, last method. I will not go into the linear discriminant analysis. I will, okay. So this is just the last method of the multidimensional scaling, because these also they will be hearing quite often. Now let me start with the example of multidimensional scaling. I will not go into the mathematical details of it. Say we have maps, right? Our earth is round, but we have our maps on the two-dimensional Cartesian coordinates. So how do we do that? How do we then, and like, measures the proximities and the distances all in the linear terms in the two-dimensional Cartesian coordinate, when my original data is actually in a non-linear complex space? If you have noticed, all these principal component analysis that we have done for the dimensionality reduction are basically the linear transformations on the data, right? We are representing the data as a set of products of different, vector vectors and their or the latent factors, or in terms of the matrix, the eigenvectors, and we are doing the dimensionality reduction. So these are all the linear dimensionality reduction methods. Multidimensional scaling is for the data when the data is itself very non-linear and complex, like we see in the map. So this is an example of the non-linear dimensionality reduction method. So, and we learned the multidimensional scaling based on the pairwise distances between the data set. So the idea is that even if I am projecting from a earth or from a spherical space or a spherical map space to a Cartesian space, the pairwise distances between the points, they should be preserved. So in the original space, how close Moscow is to Helsinki should also be preserved in my two-dimensional Cartesian space. Okay. So this is the whole idea of multidimensional scaling, that given pairwise distances between n points, dii, where dij, where I and j represent two distinct points and d is the distance between them, we need to place them on a lower dimensional map such that the distances are preserved. So typically we do it by feature embedding, but in the multidimensional scaling, a method is used which is called the Salmon modeling. So Salmon modeling is basically it is developed upon the Salmon stress or the Salmon cost function, which is used in the multidimensional scaling method. Okay. So as you can see, my Z is the reduced feature space, my X is the original feature space, and I need to learn learn the reduced mapping via some function G, such that my original distances are preserved. Original pairwise distances are preserved. So this is the basic idea of multidimensional scaling. So any question till now? Okay, so I am not discussing linear discriminant analysis, which is also called as LDA, and this Fisher's linear discriminant, all these things, which is so these like PCA is used in classification, and linear discriminant analysis is used if you see how topics from a text are learned purely in an unsupervised manner, then the linear discriminant method is used. Okay, so you will heard these terms, but it is difficult to cover all these methods because LDA itself again a complex set of derivations. So I am not going into it, and and the other methods which you may or may not come across is the canonical correlation analysis, which is generally termed as the CCA, or the isomap representation. So just let me just give uh, a basic idea about the isomap representation. So what happens? Say, do you know the distances on Earth? The shortest path is actually not the straight line. It is a curved path because we are on a curved surface. We are on a spherical space. So the distances in the actual data manifold are called, so if you see on the R distances, you will come across the term geodesic distances. Okay. So which are, as you can see, this distance between these 2 points in this actual manifold can be this. It is truly a very large distance. But as we always take our most often we take our input feature space as an Euclidean space, these distances may not be preserved. Say I want to, if I am working with data which are in a spherical space where the geodesic distance is actually the measure of the distance, like on the Earth surface. So if you search, you will see that between 2 points, actually, if we take really the geodesic distance, the shortest path is not the intuitive straight line. It is the curved line. Okay. And then in our input space, these distances, if I just plot it in the Euclidean plane, the distances will be disrupted. But we need the distances for many real world calculations, especially when I want to know the similarities or the distance between any two data points. So the isomap technique, the, the isomap technique is typically done on the graph data or the connected data to preserve these distances on an Euclidean space. Like the actual geodesic distances, we transform into the n% distance matrix on the Euclidean space, and we learn multidimensional scaling on it. No need to go into the detail of the isomap embeddings right now, but the isomap method, but just learn this to preserve the geodesic distances or the actual, what we call in terms of the graph data is called the manifold, the actual connection and the feature space. It should be preserved in the Euclidean distance. Just a moment. Hello. Hello. যা তাহলে এখন কোথায়? আচ্ছা আচ্ছা আচ্ছা, কি যা আস্তে আস্তে আমি তোকে ফোন করছি। লাস্ট, হ্যাঁ 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 ওকে। So okay, so this code you can get from the MATLAB source. I am not sure what is exactly the neighborhood graph data, like what exactly is the data set. I have not got the time to look into the data set explicitly, but as you can see from the isomap representation, so this is the off-digit data set, and the source can be, code source is in MATLAB from this web link. So after this isomap plotting, as you can see, the similar data points are grouped together, and different data points and there is, as we expect in graph, there are more connection within the similar group and less connections across the different groups. So this property is preserved. Okay. So with this, I conclude the dimensionality reduction. So we have discussed PCA, a bit of feature embedding, factor analysis, singular value decomposition, and the basic ideas of multidimensional scaling and graph isomap. So any question till now? Or today I will stop here only. So if there is any question, please feel free to ask. So